Well, good evening. So welcome to this evening's public lecture organized by the Institute for Mathematical Sciences. My name is Chong Chital. I'm the director of the Institute. This evening, we are very happy to have Professor Susan Murphy as the speaker for the public lecture. Professor Murphy is currently Professor of Statistics and Computer Science at Harvard University. She's also the Radcliffe Alumni Professor at Radcliffe Institute at Harvard. She's most famous for her work applying statistics to, broadly speaking, medicine. In fact, she was awarded the MacArthur Fellowship in 2013. Some of you probably know the MacArthur Fellowship is also popularly known as the Genius Award. So the citation of the award reads, translating statistical theory into powerful tools for evaluating and customizing treatment regimes for individuals or patients with chronic and relapsing disorders. And Professor Murphy is also a member of the National Academy of Sciences in the US, as well as a member of the National Academy of Medicine in the US. And her most recent research interest is in the area of mobile health. And this evening, she will give us a lecture on this topic. Please welcome Professor Murphy.
Thanks so much. Thank you for inviting me. It's a pleasure to be here. I had a great lunch today with our director, so it was a pleasure. So today, I will talk about mobile health, and this is a general audience talk. So if you heard my talk earlier this week, the first couple of slides are the same. So this slide is just a reminder to us about the role of experimentation in learning. If you go back to the fathers of statistics, in particular Fisher and his protege George Box, they often talk about this iterative nature of experimentation, using experimentation to continually optimize. Today, well, I guess about maybe 20 years ago, almost all of the experimentation that went on in the States, at least in the States, had to do with improving health, clinical trials, that sort of thing. But today, that's not the case anymore. Almost all experimentation that goes on in the States, I'm talking about randomized experimentation, is going on the web, on Facebook, Google, and so on. And it's being used to sell us things. So what I want to do here, and many of the people in the workshop I've been part of, our goal is to use these ideas of experimentation to improve health, to return experimentation to improving learning and health. So I want to talk first just briefly about the vast types of problems that if you're interested in sequential decisions, sequential treatments in mobile health, the vast array of kinds of areas that one can contribute to. So we have one study with a commercial company. This company sells its app to other companies, and the other companies make it available to their employees to help the employees improve their feelings of wellness and their well-being. And we ran one of the trials that I'm going to talk about today. These are called micro-randomized trials to help that company improve engagement in the app. So you can work with companies. And then there's these two studies are typical in National Institutes of Health funded studies. They're funded by researchers whose long-term goal is to advance the science and as well as produce interventions that might be rolled out in future. Sense to Stop, I spoke about this earlier this week. This is a bench research study using wearables that are not available commercially. They're all prototype wearables, and there's a large amount of data coming in. So you can work in bench research studies, more clinical, traditional clinical studies, the business area. Sarah's quite interesting. So this is a study where the goal is to collect information from young adults and adolescents who are in trouble because of their excessive drinking and excessive substance use. And you want to understand what their perceptions of stress, their perceptions of loneliness. So to understand that, you need self-report. And so in this study, again, it was a micro-randomized study, the interventions being randomized were reinforcers to try and understand how to better engage people in data collection. So there was no therapeutic aspect to the interventions. It was all about engagement and reinforcement in data collection. And then this last study is very fit. This was run in Seattle by Kaiser Permanente. And this is not a clinical research study. Kaiser has many patients that go through bariatric surgery every year. And one of the problems they're having is that many of these patients, bariatric surgery is for people who are morbidly obese. And it's a very high-risk surgery. And a big problem there is that many people gain back much of their weight within a year. This is a horrendous situation because the intervention itself is so risky. And what they wanted to do was to provide an application, so roll it out as part of their clinical practice to improve their clinical practice and how to help people be more active, eat more healthily, and et cetera. So this is not a research study at all. It's all about a healthcare system trying to improve their healthcare for their patients. So you can see the variety of areas. For example, in BaryFit, there's no consent, right? Because this is a healthcare system improving healthcare. It's not a research project anymore. So there's just a whole variety of areas that if you're interested in sequential decision-making, you can play a big role. And in all of these areas, we were involved in studies that ran these micro-randomized trials, of which you'll see shortly. So to better understand this, I want to talk about two components of mobile health interventions. There's push components. Now this is where the phone interrupts you in your daily life in an attempt to help you in some way, okay? And there's a lot of potential for this because it's well understood that when we're struggling with a chronic disorder, in times of high risk, we often are not aware that we're in that risky situation. There's a lack of self-awareness. And so if the phone could intervene at those times, it might actually be able to help you before you're able to recognize, oh, I need help. Nonetheless, the potential for negative effects is very high because it is interrupting you in your daily life. It's quite burdensome, and you can habituate to the message and not even see the messages. There's pulls. So this is another type of component on these mobile health interventions. In a pull, the support lies on the phone, and you as the user, you recognize I need help right now. You go to the phone and you pull it out of the phone. So the great thing about this is we're not interrupting you. The bad thing is you have to recognize at that moment you need help and go to the phone and access that help. I'll show you some examples of pulls, but pulls are very common across all of mobile health. For example, in recovery support for people who have alcoholism, often you can go to the phone at any time and you'll see the nearest in time and space an Alcoholics Anonymous meeting. And then you can access that meeting. So that would be a pull. You go to the phone to discover that. So today what we're going to do is we're going to really focus more on the push intervention components. And the reason why we're focusing on that is because of the potential for iatrogenic effects. The minute you have iatrogenic or negative, you could have negative effects. That's a classic setting where you want to experiment. You don't want to willy-nilly just interrupt people in their daily life. So I wanted to show you some examples of pulls and pushes. So here's Sarah. Sarah had a whole variety of components, but it also had a gamified interface. Remember, this is for adolescents, kids. And as you answered more questions, you could make your aquarium grow. You could level up to the sea. The reinforcers that were randomized were provided via this interface. They all had an aquarium kind of flavor. And a pull we might be interested in learning, well, what kind of user interface is best for which kind of person? You might experiment with that. Here's another way of providing reinforcers. A colleague of mine developed this. This is more for an adult population. The ostrich matures and lays an egg, and there's rewards in that egg. So here's an example of a push. This push was used in Sarah. The idea was, if we give you a present, will you be more likely to do something for us than if we don't give you a present? And the presents were these memes and gifts that young adolescents and young adults tend to exchange. So here's an example. It's a notification, and it comes up. This is by Selena Gomez, and it's a quote that she would give about how you have every right to a good life. It's just a little present. Other things are like little cats that get caught in little activities, and they make you feel good. So it's just little presents. If we give you these little presents, will you be more likely to answer our questions? So that's an example of a push. So today what I'm going to do is I'm going to focus on HeartSteps. That's a physical activity study. And this study, it's a series of studies. There's three studies, and we're going to talk mainly about the first study, the data from the first study. But I'm going to try and remember to tell you how the analyses of this data are leading to the 90-day study. As we go through, the 90-day study is about to go into the field now. And the 90-day study is for people who have hypertension. This first study was only for sedentary individuals. Like all mobile health interventions, they're quite complex. They have many intervention components. Here we're going to only focus on two intervention components, the two intervention components that were micro-randomized in HeartSteps. And we want to, and the whole goal, you can think of micro-randomization as a factorial design. And all factorial designs, the purpose of factorial designs is to develop an intervention. It's not to evaluate whether an intervention is better than some comparison. It's to optimize and develop. So in HeartSteps V1, we have each individual is wearing a tracker, and the tracker provides minute-by-minute step count as well as sleep quality. There's a variety of sensors on the phone. We knew how busy your calendar was at any given time, the location, your current location, the weather, and so on. And then each evening there was a self-report about your perceptions of stress and how burdened you felt the intervention was. And there was other questions as well. So two of the big questions that we wanted to ask was, how might the smartphone help you plan your physical activity tomorrow? And then a second question was, so this is the first factor in the factorial study. And the second factor was, in which context is it worthwhile for the smartphone to interrupt you and provide a tailored activity suggestion? I'm going to show you examples of these. So let's look at the tailored activity suggestion first. So what would happen is your phone would ping and you'd get a notification. And that notification is tailored to where you are, what the weather's like, home, work, time of day, day of the week, and so on. And it's intended to be actionable in that context. There's two types of activity suggestions. One that's more onerous, takes about 3 minutes. The other is great. It makes you feel good because you just stretch your toes or something and you just feel really good. It's more engaging. There were also two types of support to help you plan your physical activity the following day. One of which was more onerous. I had to sit there with my thumb and enter a operationalized plan of how I was going to be physically active tomorrow. It's a big hassle. The second was populated with plans that I had already made out, my own plans. And I just had to choose one of them. It was much easier on me. So in both of these cases, this occurred, we'll see this occurred every evening. We were interested in, should we provide evening planning? And this could occur during the day. You'll see this in more detail as we go through. I'm going to focus mainly on the within-day physical activity suggestions, but I'll touch back to the evening planning at the end of the talk. So what I want to do now is, if this were an audience of behavioral scientists, I spend a lot of time on this part. So this is all about designing the experiment. An enormous amount of science, domain science, goes into the design of these experiments. And I'll indicate that briefly as we go along. So the first aspect of the design is at what points, time points, might you potentially provide an intervention? Might you potentially provide an activity suggestion? These are called decision points. Normally in our studies, they tend to be at regular intervals in time. We try usually, at first pass, we usually want them to be every minute, because if they're every minute, then from the user's perspective, it will appear as if an intervention can come in real time. Just because it's every minute doesn't mean every minute you're getting a ping. That's not where, it's just that it could appear to arrive at any given minute, or at user demand. In HeartSteps, originally we were going to go every minute. Because every minute we were going to have the potential to provide a message. But then we had access, the tracker was a jawbone tracker, and we had access to a large number of jawbone users who were in the same age group as the people who would be in HeartSteps. And we found that when you looked at their within-person variance in their physical activity, the highest variability, within-person variability in their physical activity occurred relative to their work schedule. And I list these 5 times. So the fact that they have high within-person variance, that indicates that there's a potential to increase their activity at those times. So instead of just willy-nilly at any minute potentially sending a message, we just chose these 5 times. Of course, these 5 times depend on the person. Each person has a different work schedule. So I just give you English names for the 5 times. So in this case, for HeartSteps with the activity suggestions, it's a 42-day study. There's 5 times a day. So it's around 210 times over the course of the 42 days you might get a message. So the choice of the decision point depends on science. It just doesn't come out of thin air. That's the point. The observations at each decision point, they are usually of 2 forms. They're sensor data that's streaming in at multiple scales in time, depending on the battery on the phone. And then there's also self-report data, and that's usually at a much coarser time scale. In HeartSteps, it was just in the evening. And I list some of the examples of the types of sensor data. Often the observations are outputs of algorithms, classification algorithms or prediction algorithms. In many of our studies, they are outputs of algorithms. Predictions of risks, classifications of your current activity, weather, location, and so on, busyness, and so on. And then there's the interventions or the treatments. That's, in our case, these are these activity suggestions. Normally when we work with teams, the behavioral scientists are most interested in different types of messages. Or different types of engagement strategies. However, here, at least initially, I'm going to focus on whether or not to even reach out and push a message. And the reason why I'm doing this, there's two reasons why I'm doing this. First is the iatrogenic nature. Remember, you're intervening in a person's daily life. And again, the potential for burden and disengagement is quite high. Also, we know if you give a lot of stimuli, repeated stimuli leads to habituation and you don't see the stimuli anymore. So that's one reason why I'm going to focus on this second type, whether to provide a push at all. The other reason is, as a statistician, I know that we tend to have higher signal between something versus nothing, as opposed to two active options. So if I'm going to plan this study, I'm going to go for a high signal type event. Okay, so let's focus at first on HeartSteps, on whether or not to provide a tailored activity suggestion at each of those 5 times. And here's a more detailed example. You'll be able to see the writing better than the last slide. So this happened to me. It was an early morning. It was pretty cold outside, actually. It was a work day. And it says, hey, look outside. It's not so bad. Maybe you should just walk to work today or park a bit further from work. So it was related to where I was in my life at that time. I could swipe away this notification by pressing thumbs down. I didn't find it very useful. I could press thumbs up to swipe away the notification. I thought the message was useful. Or I could press the middle button. If I press the middle button, a drop-down menu would appear, and I could turn off the intervention, all of these notifications, for up to 8 hours. This is great. I, as a user, have control. In fact, at any given time, I could turn off the interventions. I think this is really critical in mobile health, to allow the user that option. So that brings into this whole notion of availability. And when I first started in mobile health, I thought, I wasn't thinking about all the iatrogenic effects of interrupting people in their real life. And so I was hoping we wouldn't have to deal with this at all. But now, as I go through, more and more of our studies are using this notion of availability. And that is that in certain settings, it is completely inappropriate for you to interrupt the person. So, for example, in HeartSteps, if the sensors on the phone indicate that you might be driving a vehicle, we will not interrupt you and possibly distract you from driving that vehicle. That's ethical reasons. Now, all of the messages in HeartSteps were about engaging in a new physical activity. So if the sensors on the phone indicated that you were currently physically active, currently walking, we're not going to bother you and suggest you do something totally different. It doesn't make any sense. Now, one of my postdocs did another study, a physical activity study, where all of those suggestions were about extending your current physical activity. In that case, we wanted to detect if you were active, and those were the only times we'd send you a message. So availability depends on the kinds of messages you might send. You might be thinking about sending to that individual. So here, we don't want to bother you if you're currently active. And another way you could be unavailable is if you've turned off the intervention. You don't want to be bothered. In any of these cases, we know about that before we even consider sending a message, a notification to you. So this is known prior to any decision about sending a notification. It's pre-treatment. Wait, did I put this? Oh, yeah, I have to say this. It's not the same as non-adherence. When I was trialing this particular intervention, I was extremely non-adherent. I would hear my phone ping. It was in my backpack. I'd hear it ping. I wouldn't even pay attention to it. That's after intervention delivery, right? Non-adherence is post-intervention delivery. It's not pre-intervention. And availability is known before a decision is made about whether or not to send you a message. This notion of a proximal outcome. So almost all of these interventions, we hope that you're going to remember the suggestions we provide to you and use them later in life. And indeed, to this day, I still use one of the suggestions that I got when I was trialing this intervention, to stand up whenever I'm having a conference call. I highly recommend that. It's a good way. But for the most part, these interventions are intended to impact you in the near time. And that's why they're tailored to the current context you're in. So when you think about an outcome, you're thinking about some near-time behavior. And in the teams, in the behavioral science teams that I've been part of when we're designing these studies, we have enormous arguments about what constitutes near time. You don't want it too soon, too short over an interval of time, because then the person won't have had time to act on any kind of message. However, if you wait too long, too many things happen in that person's life, and you get too much noise, and you're much less likely to see a signal. So there's a lot of domain science that goes into these, a lot of domain science and a lot of argumentation that goes into these decisions. In HeartSteps, we decided 30 minutes because we were concerned that if we waited too much longer than 30 minutes, you'd leave your current context and the message didn't make any sense anymore. I just said this, that suggestions are designed to be near-term actionable. And so when we were designing this study, and in fact, when we determined the sample size for this study, our primary question was, do these suggestions have any impact on you at all in terms of your activity in the near term? Is there a signal here at all? Is anything going on average, across the study? Is there a signal? And then the second question we wanted to address was, does this effect, if at all, if you have an effect at all, does it deteriorate over time? And why were we so concerned about the effect deteriorating with time? Because of the issue of we're intervening in the context of your life, and you're going to potentially get aggravated, delete the app, or habituate, and not even see these notifications when they come on your phone. So these were the primary questions, and when we sized the study, we actually sized it for the second question. Of course, that gave us greater power for the first. So I want to go over what a treatment effect in this setting. Okay, again, we're going to randomize each individual at each of those 5 times. We'll first check if they're available. If they're available, we're going to randomize them each of those 5 times over 42 days. So that's up to 210 times, depending on availability. And then and that's just one of the factors in this factorial study. So each factor is a time-varying factor. What's a main effect for these factors? What do you mean by an effect? So I have a little picture here, and this effect you might imagine is time varying. And this is a really coarse description. In fact, when we were thinking about the study, I actually drew this curve. So there's 210 on the horizontal axis, because that's 42 times 5 times. And then the vertical axis is a standardized effect. This is a signal-to-noise ratio. It's an effect divided by a standard deviation. So when you think of an effect, how many standard deviations might I move you? And this is very small effect sizes, because at the time we were designing this study, it was the second micro-randomized study, and I didn't really understand what kind of effect sizes you might have. Nonetheless, I drew this curve. So what was I thinking? I was thinking early in the study, everybody's very confused. They just got this app on their phone. They won't even notice it. They're just too confused. No treatment effect at all early in the study. So that's why we're close to 0 here. And then as the study goes on, people become engaged, and they try, the suggestions when they get a suggestion, and they don't do anything when they don't get a suggestion. So you get an increasing treatment effect. This is what I was thinking in my mind. And then, unfortunately, as time goes on, they habituate, and they don't even see our notifications anymore. They're not there anymore. They don't see them. And so the effect deteriorates. That's one way you could interpret this curve. I'm going to give you a second way for you to interpret the curve. So at the beginning of the study, everybody is pretty much available, except for the driving. And I'm going to ignore driving. It occurs around 20% of the time. I'm just going to ignore it. Another reason why you might not be available is because you're currently walking. So anybody who really responds to this intervention is highly likely to end up being walking. And we won't be able to randomize them, right? They won't be available because they're walking at those times. They drank the Kool-Aid. So at the beginning, everybody's pretty much available. We go through time. The subpopulation of individuals that we're experimenting on is evolving through time. As you go farther, some people really get engaged, and they're no longer available. Who is left? Who is left in our subpopulation? The most treatment-resistant individuals. So then again, you might see a decrease in the apparent effect because the subpopulation at the end of the study that you're experimenting on is the most resistant to the treatment that you're providing. Very interesting. So you can have a time-varying treatment for two reasons. One, because your subpopulation of individuals is evolving as a consequence of prior treatment. And two, because the treatment effect, people get habituated and everything deteriorates. Now, in this particular study in HeartSteps, we didn't power it to look at this issue of availability and people becoming less available because they were walking. But we didn't see any indication of that anyway, but it wasn't powered to see that. So here, when I show you the data analysis, you will in fact see a downturn. It was amazing, we conjectured that, and we suspect that's mainly due to habituation. Okay, so this is repeating what I said before. At every one of those 5 times a day, over the 42-day study, each person is randomized to either get a suggestion to be active at that time or not. And when we first designed the study, we were thinking we wanted to send around 2 messages per day on average. And then, as is always common in trials, you always run the study with about 10 people or so ahead of time. And then we discovered that so with 2 times a day, that would be 2/5 randomization. That would be 0.4. With probability 0.4, you'd get a treatment, 0.6 you wouldn't. But then when we ran 10 people going through, we noticed that around 20% of the time they were driving. They weren't available. And so we changed the randomization to accommodate that so that still, on average, 2 times a day, people would get a message. So in all of the micro-randomized trials I've been in, they're always subject to a budget, a constraint, an average number of times you want to intervene, and most of the time this is due to considerations of burden because you are interrupting these people. This means that rarely, if ever, do you get randomization of 1/2. In fact, in this smoking study that I spoke about this week, we have thousands and thousands of decision points. The randomization probability at any given decision point is very small indeed. The probability of getting an intervention. Okay, so what I'm going to do is I'm going to talk to you about some of the data analyses that might go on after you run this. And I'm going to do this in a way, this is the way I explain this to my behavioral science colleagues, domain scientists, and actually I find it helps me as a statistician be clearer about what I'm really doing and what my objectives are. Okay, so in clinical trials, there's a protocol that people run that when they go through and do the data analyses. It's pretty traditional how data analyses are done in clinical trials. So let's imagine that we have a trial at each time point just to get our mind straight. And the first analysis is always, is there a treatment effect at all? AT is coded as 1 if there's an activity suggestion and 0 otherwise. And we're going to go through this in greater detail. And then the second analyses are always about moderators. So among certain people, maybe they'll be more responsive to the intervention than others, and we want to understand that because you might want to just give the intervention to those people and not to others. So this is a classical way of thinking with clinical trials, and I want to unpack that because when you go to these settings where you're micro-randomizing, you really need to understand where you're coming from. Okay. So these are conceptual models. I'm not fitting linear models. That's the reason why there's this little tilde and quote. This is just to help us get our ideas straight. So first I want you to focus on the blue parts of these models. So this is not about science, domain science. This is about data science. The blue part of the model is all data science. It's all about increasing the signal-to-noise ratio so that we can more clearly detect effects if they, in fact, occur. And in fact, mainly, these are often, this variable that I'm indicating by Z, these are often called control variables because you're trying to control the variance, reduce variance, increase the signal-to-noise ratio. One of the best control variables there is the pre-treatment measure of the outcome. So if you can measure the same outcome prior to treatment, that really reduces variance and increases the signal-to-noise ratio. So people always try and measure like severity of the disorder prior to randomizing to treatment, and then they put severity as a control variable. That's classic. No domain science, only data science. Then now the part of this part of the model is where the domain science, the behavioral science in mobile health comes in. And so the first analysis, again, AT is an indicator 1 if you get a tailored activity suggestion, 0 otherwise. So this coefficient of AT, it represents an effect. AT is randomized. This is going to represent a causal effect. And let me talk about how we, in traditional clinical trials, interpret that causal effect. We all know this causal effect is marginal because we're not controlling for gender. We don't have different effects. We're not looking at different effects for gender across men and women. We're not, in HeartSteps, for example, we wouldn't be controlling for the time of the day or the weather outside or whether I'm at home or work or how sedentary I was before I came into this study or whether my mood is not so good today or bad today. These are marginal effects averaged across the variety of contexts that the person is currently in, the variety of personal traits that that person has, but they're still causal. We have randomization here. So it's a causal effect, but it's marginal. And it's even marginal over unobserved variables. Like in the behavioral sciences, our field is relatively immature, and we often don't even measure or observe things that actually might be important because we don't know what to observe all the time. But we understand. So beta 0 is the effect of the tailored activity suggestion, marginally over all observed and unobserved variables. Then we start unpacking it. So that's our first analysis. Our second analysis and third and fourth is an unpacking of that effect, trying to get closer and closer to subgroups of individuals. So here I have ST. In my case, I'm looking to see whether or not, I just made this simple here. It's binary. ST is 1 if the current weather is good, 0 otherwise. So now I'm looking at 2 regression coefficients, beta 0 and beta 1, and the combination of those is the effect of getting a message versus not when the weather is good, right? That's what it represents to me. It's still quite marginal. I didn't include gender. I didn't include whether or not you were at home or work. I didn't include time of day. I didn't include whether or not your mood was good that day or not. But it's still causal. but it's getting closer to the current context of that individual. And as you can well imagine, if I have the more data I have, the more variables I can put in here and get closer and closer to that current individual's context. Now, with a limited amount of data, I can never get absolutely at that person's context. I never will. And in fact, in the behavioral field, we don't know everything that's important in that person's situation at that moment in time, and so we may not even measure all of it. So no matter what, whatever effect I give you here, it's still marginal, but it's causal. So when we analyze clinical trial data, we always know we have a marginal effect, but we have a causal effect too, because we're using randomization. So when we go to develop methods to analyze these kinds of micro-randomized trials, in our mind, we're looking for methods that give us similar kinds of interpretations to the interpretations I gave you on the last slide. The challenges here, though, are that our treatment is time varying. Indeed, whether or not I'm even available for treatment at time t is probably an outcome of how much I got treated in the past. So we have this time-varying treatment, many treatments, 210, in fact. And my independent variables, the variables I want to do to increase the signal-to-noise ratio, the control variables, they're not independent. They're not pre-treatment, because they could have been impacted by prior treatment. So one has to be very careful in these settings not to produce causal problems where you pick up correlations that are not causal effects. And the last thing we want to think about as we develop a method is we want to robustly facilitate noise reduction, i.e. increase the signal-to-noise ratio if there is a signal, via use of controls. And what would be a natural control in HeartSteps? Well, the outcome is the subsequent 30-minute step count. A natural control is the pre-decision point 30-minute step count. Man, that's a great control. That's highly correlated with my outcome. That's going to really help my signal-to-noise ratio. But my pre-treatment 30-minute step count is probably impacted by prior treatment, as is my availability, which is this indicator here. So we got to be able to manage that. So we developed this method. Actually, I say it's simple method for complex data. If you've heard me talk about this method, it wasn't simple at first. It was extremely complex and quite cool. And we were very excited about it because it looked very machine learning. And but then we got a number of review comments, and we realized that we could make this method very simple. And the travesty about this is now all my behavioral scientist colleagues, they don't need me to analyze their data. It's a relatively simple method. But it's great. It enables unbiased inference for these causal yet marginal treatment effects. And the inference for the treatment effect is not biased by how we use the controls. Now, this is really important because there's an enormous amount of data that you might want to use to increase the signal-to-noise ratio here. So you don't want to depend on you using these controls, modeling them in a good way. You don't want to waste degrees of freedom here. So I'm going to show you an application of this method in the primary analyses of HeartSteps. Here's a schematic of HeartSteps. I already mentioned to you this is a factorial design. There's 2 factors. The tailored activity suggestions, that factor, the time scale for that factor is 5 times a day. The randomization is 0.6 to message, 0.4 no message at all. We don't bother you. The other factor is every evening, and this is you get randomized to providing support to plan your next day's activity or not. And that's randomized with probability 1/2. So that's at the evening time scale, and the other is at 5 times a day time scale. This is really common in mobile health. You have multiple factors. In some studies, we have like 6 factors, and each one is at a different time scale. And you see in this schematic the outcome The proximal outcome for the 5 times a day is the 30 minutes step count. The proximal outcome for the daily is the next day's total step count. So it's a very interesting experimental design. I'm going to focus first on providing a suggestion versus doing nothing. So that was the primary analysis of this study. Do we have any signal at all? There's up to 210 times each person is randomized. So this is the conceptual model. This is not, we didn't actually fit this linear model, okay? I have to warn you, it's a conceptual model. And I'm gonna focus on the estimators of the treatment effect for 2 settings. One is the overall marginal effect. Is there any signal here at all of getting a message versus not on your subsequent 30-minute step count? And the other is going to be about a deteriorating effect. I'm going to talk to you about that. So my outcome is going to be log transform step count. This is because step count is highly skewed. And using a log transform allows us to use the confidence intervals will be more accurate. A, again, is 1. If you got a message, you were randomized to a message, 0 otherwise. We're going to control, we only had 1 control variable, your prior 30-minute step count. This was all pre-specified. It was registered in clinicaltrials.gov before the study was run. It's set in stone. It turns out we did sensitivity, and there's no need to do any, this really picks up the noise, this particular control variable. DT is the day in study. On the first day of the study, DT is 0. The second day of the study, DT is 1. There's 42 days, so the last day of the study, it's 41. So let's discuss this analysis here. Why did we put DT here? What are we thinking? Okay, we're hoping this beta 0 is going to be a positive number, because that would mean that we get a signal and that people walk more after they get a tailored activity message versus if they don't. That would be wonderful. But I was really concerned about deteriorating effects. Actually, originally, we sized the study for a quadratic trend, and then we decided before the study was run, we didn't want to waste the degrees of freedom, and we went for a linear. Because it's just approximate. There's no way it's actually linear. This is an approximation. We're doing a bias power trade-off to get more power. Anyway, so what does this mean? I figure this is, so beta 0, when DT is 0, this term is not there. So now beta 0 becomes the effect of the message on the first day. It's a proxy for the effect of the message very early in the study. And unfortunately, we conjectured that this coefficient would be negative because people would habituate and the effect would deteriorate. This is what we conjectured. So now we're going to see the analyses. So I have to interpret these analyses because it's all on the log scale. So the actual regression coefficients are not interpretable. So first, the overall effect here. This is this beta 0 here. This coefficient is 0.13. It has no meaning because it's on this log scale. It translates into an approximate 14% increase in step count. In the 30 minutes following a step count, you get around, in any 30-minute interval, you get around 250 steps. It translates to about 33 more steps if you get a message versus not. That's what this first one is. 95% confidence interval just barely gets into the negative. Then we do the second analysis we pre-specified. So here, this encapsulates the effect early in the study. It's a proxy, an estimator of the effect early in the study. 0.51, this is an enormous effect. It corresponds to approximately a 67% increase in step count. So going from around 250 steps to 250 plus 170 steps, massive impact. And then you think, well, you see this negative 0.02, you think, well, it's very small, it must not have, it's bad. It's bearing out my conjecture that everything is going to deteriorate with day in study. But you think, oh man, it's not too bad, it's only minus 0.02. But you gotta remember, this is compounding with time. This is a 6-week study. By 3 weeks in, halfway through the study, nothing is going on. Nothing. So how did this impact the next HeartSteps? In the next HeartSteps, we have an online algorithm that's constantly altering the randomization probabilities. And when when it appears as if people are starting to become less responsive to the intervention, it backs off. It reduces the probability of them getting a treatment. And then if they they appear to start being more responsive, it increases the probability of them getting. It's a 90-day study, so we'll have a lot more time for the probabilities to back off when they stop being less responsive, allow them to dishabituate, and then come back again. And that's a result of this analysis. It turns out there were 2 different types of activity suggestions here. One was a tailored walking activity suggestion. This is about 3 minutes. I mentioned that earlier. It's a little bit more burdensome. It takes me 3 minutes to act on. The other was very engaging. It would be like, why don't you just stand up and roll your arms? Everybody. We did a lot of exit interviews with this study, and the participants love these. Because you felt really good, man. You stood up and rolled your arms. You feel really good. You've been active. So what we did is if you were randomized to an activity suggestion, you got equally randomized between the one that was very low burden, you feel good, and the one that was higher burden. Now, the reason why we did this was because past 2-arm studies who did not look at factors, did not do micro-randomization, they suggested that if you just got people to stand up, they would then become more physically active. That's the reason why we had these 2 alternatives. One was a direct request to become physically active. The other was just a request to stand up and move just a little bit. Okay. This now is not the primary analyses anymore, okay? We're getting into secondary analyses. We have 2 indicators of treatment here. This indicator is 1 if you got the more burdensome intervention delivered to you, the walking suggestion, 0 otherwise. This indicator is 1 if you had the less burdensome intervention delivered to you, 0 otherwise. So beta 0 is for the more burdensome. It was the only one, actually the p-value here I think was 0.85 or something. So what does 0.21 translate to? Around a 23%. So this is an average over the whole 42 days in terms of an average effect of getting a more burdensome message versus anything else. So it appears that most of the effect of the activity suggestion is really due to the delivery of the more burdensome activity suggestions. We also interacted this with time. I'm not going to show you that analysis. It's just low level, but I'll just give you the results. The data indicates there's a causal effect of the activity suggestion on the step count in the succeeding 30 minutes. The effect appears primarily due to the more burdensome activity messages. This was a big deal. The effect, unfortunately, deteriorates with time. By about midway through the study, gone. The walking activity suggestion, so when you interact this with time, early in the study, the increase was around 271 steps. That's more than a doubling of what their normal activity would have been at that time point. Big effect. But by 3 weeks out, day 20, 21, you can't, I said 65, but this is not significant. There's just nothing going on anymore. Again, that habituation issue. We also did this with the evening planning for the next day, and I'm just going to give you the results. I won't go through this whole story, but I think it's really interesting, particularly from a behavioral science point of view. And you and me, because we may very well be subject to experimentation if we download an app a health app from the Google Play Store or on your iPhone. So I just want to tell you about what turns out to have more evidence of efficacy here. So here it was the more burdensome suggestion, right? But it deteriorated because we just had this constant probability. So now in the evening planning, that was about planning your next day's activity, there were two types of planning we had if you got randomized to planning. One was unstructured, much more burdensome. I had to use my thumbs and type into my phone. It was a total hassle. The other, I got a list of my own ideas from prior days. Not Bebosh's ideas, my ideas. It was great. I didn't have to think much. I just picked one of them. And then we didn't bother you at all half the days. I tell you what happened here. The data, again, we got an effect. It was fantastic. There was an effect, a causal effect of planning the next day's activity on the following day's step count. The effect is mainly due to these unstructured, the ones where I had to sit there with my thumb and be aggravated while I'm doing this. The behavioral scientists, now this is all after the fact, the explanation I'm fixing to give you is after the analysis, right? And one can always make up explanations after an analysis comes in. But they believe that because you put in so much cognitive burden into planning your next day, you were more likely to actually actuate that. Then a subsequent analysis, it appears that most of that effect is when you're planning for a weekday, not planning for a weekend. Weekends tend to be much more chaotic. And planning for a weekend didn't appear. But the study was not sized for this, so I can't speak to the replicability of that. I just want to have a couple of slides. Bebosh, are you keeping track of the time? I started late, but I want to end not too late. Yeah, I should stop soon. So, okay, I just want to show you this last slide. If you had come to me before I started down this path, I would have used some sort of machine learning method to analyze this data. Or I'd have used classical random effects models even. That's really common in mobile health. We love random effects models. A machine learning, maybe a partially linear single index model. It's a nice machine learning varying coefficient models. The problem is these models they're great analysis methods, but they were never designed to do causal inference. And in fact, because the way they try to increase the signal to noise ratio is they use future data to inform the estimate of the effect at the present time. And if you do causal inference, you know the one thing you should never do is use the future to estimate a causal effect at the present. So you can accidentally produce, here you are in this randomized trial, and you produce confounding when you shouldn't have had any confounding because you had a randomized trial. I was going to go through, I think I'm out of town, so we have all these schematics of how we ran these trials. This is my last slide. I just wanted to emphasize that these types of trials, they require big teams, computer scientists, behavioral scientists, human-computer interaction, people like Joseph in the back, statisticians, app developers, tons of people have to come together to run a study of this type. It's big science. It's not. So thank you.